Hello friends, let us continue the part. We are going to find eigenvectors. So here the given matrix is a symmetric matrix, all of you note. So let us calculate the trace of this matrix first. Trace is equal to sum of diagonal elements, which is 12. SMD, sum of minus of diagonal elements, which is 36. As usual, what we have done in the previous example, same procedure we are going to follow to calculate SMD, and the determinant is equal to 32. After finding all these values, we have to write the characteristic equation. We know the formula, lambda cube minus trace is 12. So lambda square plus SMD is 36 lambda minus determinant of A, which is 32, equal to 0. So if you solve this equation, we will get lambda is equal to 2, 2 and 8. So here one of the eigenvalue is repeated twice, that is lambda equal to 2. Now let us find the eigenvector associated with lambda is equal to 2, which is repeated twice. So substituting lambda is equal to 2 in the equation a minus lambda into x is equal to 0. So here you can put lambda is equal to 2, means you need to subtract 2 from diagonal elements. So 6 minus 2, diagonal element is 3, 3 minus 2 in the second row, and in the third row 3 minus 2. So this equation becomes 4 minus 2, 2, coefficient matrix, minus 2, 1, minus 1, and 2 minus 1 and 1. Now we have to reduce this to this matrix to row echelon form. Okay, so use the transformation. I'm going to use here transformation, which is 2 times R2 plus R1 and 2 times R3 minus R1. So if you do this transformation, the above equation, matrix equation, is reduced like this: 4 minus 2, 2, and next second and third row of the coefficient matrix becomes 0. Now there are some results. We know that the number of non-zero rows in reduced row echelon form, so this is the reduced row echelon form, and the number of non-zero rows in the reduced row echelon form is the rank of that matrix. All of you note down this. So here there is only one non-zero row in the reduced row echelon form, so its rank is 1. So I'm going to denote rank by R, so rank is 1. Also, there is one interesting result. If the rank of the coefficient matrix A is equal to the rank of the augmented matrix is a matrix, we have to add this column to the existing matrix, it becomes an augmented matrix. So if you add 0, 0, 0 column, the rank is not going to change. So rank of A and rank of augmented matrix is same here, and which is less than the number of variables. Here x1, x2, x3, these are the 3 variables. So n is equal to 3. So R is less than n. So the system has infinitely many solutions. So similarly, this equation has infinitely many solutions. To calculate the solutions, we are going to use the formula. Number of linearly independent solutions is equal to n minus r. So n is 3, r is 1. So here 2 linearly independent solutions. So I'm going to consider here, we know we got the number 2. So I'm going to consider here x2 as s, one of the arbitrary value, and x3 as t, second arbitrary value. So after finding these arbitrary After considering arbitrary values x2 as s and x3 as t, we have the equation here. If you write this given matrix equation into linear equation, there is only one equation, 4x1 minus 2x2 plus 2x3 is equal to 0. Here you can divide by 2, so you will get 2x1 minus x2 plus x3 is equal to 0. Or you may write here twice x1 minus s plus t is equal to 0, or x1 is equal to s minus t divided by 2. Now, to find the eigenvector, we have to choose s and t as some arbitrary values. So I'm going to consider here, let s is equal to initially suppose 0 and t is equal to minus 2. You will get one of the eigenvector here x1. You can put s as 0 here and t as minus 2. Minus 2 divided by 2 is minus minus plus, so this is equal to 1 here. So x1 is 1, and you know that x2 is itself s, x2 is itself s, so this is 0, and the value of t is minus 2. So one of the eigenvector associated with lambda is equal to 2 is 1, 0 and minus 2. Now you can switch, put s is equal to 2 now and t is equal to 0. So you will get another vector, because uh, we know that there are two linearly independent solutions. So if I put s is equal to 2 here, t is 0. So 2 by 2, which is equal to 1. So x1 is 1. x2 means s, which is 2. And x3 is t, which is 0. So second eigenvector associated with lambda is equal to 2 is 1, 2 and 0. So here lambda is equal to 2 is repeated 2 times, and we got two independent, linearly independent eigenvectors also. Now lambda is equal to 8, which is one of the eigenvector, and we have to find eigenvector associated with this, one of the eigenvalues, sorry. So here I'm going to repeat the procedure now. For lambda is equal to 8, you have to put this value into, you have to subtract 8 from the diagonal elements into x is equal to 0. And we know that we have done so many times, if the eigenvalue is not repeated or non-repeated, we can use the Cramer's rule, and definitely we will get one vector associated with this. So if you solve this using Cramer's rule, you will get a vector which is 2, minus 1 and 1. So in this way, here lambda is equal to 2, which is repeated 2 times, and we got two linearly independent solutions. All of you note down, this is very important. And for lambda is equal to 8, which is non-repeated, so by Cramer's rule, we can find one vector associated with this. Okay, I hope this example is clear. Now we will move to the next example. So you can see this example. We will calculate again normal procedure. Trace is 4 plus 3 minus 2, which is equal to 5. If you calculate SMD, same procedure. SMD is 8 here, and determinant you can calculate using calc also, which is equal to 4. Uh, Characteristic equation lambda cube minus 5 lambda square plus 8 lambda minus 4 equal to 0. Enter this equation in calc. You will get lambda is equal to 1, 2 and 2. So all of you remember here 2, one of the eigenvalue which is 2 repeated 2 times again. So again, first I'm going to calculate for lambda equal to 2 only. So you can put this value in the equation a minus 2i into x is equal to 0. Means you can subtract 2 from the diagonal elements. So which is 2, 6, 6. Then this is 1, 1, 2, minus 1, minus 5 and minus 4 into x1, x2, x3 is equal to 0, 0, 0. Now we have to reduce this matrix to reduced row echelon form. So I'm going to reducing it to its row echelon form. Row echelon form. So you do some calculation, which is twice R1, R2, twice R2 minus R1 and twice R3 plus R1. So if you apply these two transformations, your equation becomes your equation becomes matrix equation, which is 2, 6, 6, and if you apply the transformation, which is 2 times R2, 2 minus 2 will be 0 here. So 2 minus 6 is minus 4. Then this will be 4 minus 6 is minus 2. Second row is 0, minus 4, minus 2. And third row is also 0, minus 4 and minus 2 itself. So into x1, x2, x3 is equal to 0, 0 and 0. Now do one more calculation, operation R3 minus R2, and you will get 2, 6, 6 and 0 minus 4 minus 2 and 0, 0, 0. All of you remember here there is, this is a very interesting step. So here this is reduced row echelon form. So here rank is equal to 2 and n is 3. So rank is 2 and n is 3. So number of linearly independent eigenvectors denoting S, that is n minus r, that is 3 minus 2 equal to 1. So this has only one eigenvector. So we know that if we have two equations, we can use the Cramer's and we can find that vector by the normal procedure of Cramer's rule. So if you apply Cramer's rule for this, so x1 divided by minus 12, I'm going to apply the rule, plus 24, and x2 divided by minus 4 and x3 divided by minus 8 is equal to proportionality constant k. So x1 divided by 12, which is x2 by 4 and x3 by minus 8 is equal to k. So if you simplify, we will get a vector. You can take k as 1 by 4. So this will be 3, 1 and minus 2. If you take k as 1 by 4. So in this way, all of you note down here lambda is equal to 2 is repeated 2 times, but we got only one linearly independent eigenvector. Okay, even though here lambda is repeated 2 times, we got only one independent eigenvector. Now for one, there is no problem at all. You can use the same logic here, and by using the Cramer's rule, we can find the vector associated with lambda is equal to 1. There is no doubt about it. We can use the Cramer's rule, and if you simplify, you will get a vector which is 4, 1 and minus 3. This is for lambda is equal to 1, which is non-repeated. So in this way, we have seen two examples here. In one example, if you see the previous example, in one example, we have seen here lambda is equal to 2 is repeated 2 times, and we got two different linearly independent eigenvectors. And in this example, lambda is equal to 2 is repeated 2 times, but we got only one linearly independent eigenvector. So this is the main difference, all of you remember. So actually, if eigenvalue is repeated, then we have to reduce into row echelon form, reduce to row echelon form, and we have to decide the number of eigenvectors associated from the difference n minus r, that is equal to s. So thank you. All of you note down these two are very important examples for exam point of view. Thank you very much.